You can still see my title slide, right?
Yeah, I can. Yep, looks good.
You can? Okay.
All right, great. All right, so we'll just just kick things off just with introductions of myself and Neil. So one, thanks for joining. And first off, just to let you know who I am, in case you haven't met me before, my name is Kathy Howard, and I am the new Global Account Manager for ADI. So previous to me was Cindy Heggie, who maybe some of you guys see around recently, as she's now a contractor for us, doing some asset utilization program for us. And after Cindy, Joe Carr was the Global Account Manager, and I took over as of November 1st. So with COVID, haven't had a lot of opportunity to be on site and to meet a lot of people, but I am local. I'm based in Massachusetts, and hope soon to be making visits to you locally there. And then Neil, I'll let you introduce yourself.
Hi, everyone. My name is Neil Hoffman. I'm a digital product specialist. I'm actually based in Pennsylvania, but support the New England area. And pre-COVID, I was there basically every other week. I've been to spent more time in Wilmington than Chelmsford, and I support Kathy for what we call our digital portfolio, which is scopes. If anybody still remembers or uses logic analyzers, bit error rate testers, arbitrary waveform generators, etc.
Great, thanks, Neil. And then today, so we've got a presentation for you on oscilloscopes today. If you do have questions, you can put them in the chat during the during this webinar. Neil's probably going to pause about halfway through to check in and either answer some of these questions, or if you have any questions you want to ask live. And then we'll have a poll at the end where you can make some comments on what you might want to see in the future. So I don't know if there's any other comment, if anybody has any comments before we kick this off. Okay. If not, then Neil, why don't you take it away?
All right, very good. So today we're going to cover modern day oscilloscope measurements. This was originally cast as an in-person lunch and learn. So I didn't actually remove those slides, but there's actually labs, which we'll sort of skip through the slides when we get to that portion. But hopefully, later this year, if there's interest, we can come and do this again on site and maybe customize it with, the oscilloscope of most interest to you folks. So just wanted to let you know that's why you'll see labs in there, because we generally like to do this in person and provide lunch if it wasn't a pandemic. So. Okay, so here's what we're going to cover today. Again, I'm not sure of everyone's familiarity with using scopes versus other types of test equipment, but we're going to cover, start with the basics: sampling, bandwidth, triggering, probing, and, kind of do some, the lab stuff. Again, we'll have to skip over that since it's virtual here today, but talk about some concepts for measurements and triggering and some of the more advanced features that scopes can do today, like protocol decode, which wasn't available, many years ago. All right, so again, here's our agenda. Again, the labs we'll sort of skip through, maybe just cover a point or two out of the lab. And we'll have a, again, I'll kind of pause when we get to the lab section, see if we have any questions then, and then we'll have a question, session at the end. So please put your questions in chat. Kathy and Leslie are going to monitor those. And again, we'll take a break in the middle and then at the end to cover questions. All right. So we got to give you a commercial, of course. So here's our commercial. Here's our portfolio of scopes. And you can see there's many different form factors, real-time, sampling, and also different physical form factors from sort of lunchbox bench, the Infinivision on the left, your more traditional Windows-based scopes in the middle, and then on the right, we have some new platforms that have been developed in recent years. USB scopes that hook directly to a PC, and then also modular, like based on a Pixie chassis. And there's more being developed as we go. So as far as, again, the three main types, USB, again, is relatively new. Whoops, sorry about that. The benchtop, again, more of the lunchbox types, and then also the types of built-in PCs. And then on the right also is relatively new with Pixie-based oscilloscopes. They're very good if you have an automated test system. There we go. Automated test system where you're combining it with other instruments, or we do have an 8-channel oscilloscope out today, but if you need even beyond that, the modular form factor would be the way to go. Pixie chassis can handle, I think, at least 10 slots, a Pixie mainframe, and you can see 20 plus channels with the modular oscilloscope platform on the right. So when we do this in person, we base it around one of our Infinivision scopes, either the one second from the right or the one on the right. So these have a built-in operating system. It's actually Windows CE embedded. So they don't have a PC or a Windows file system that you can access per se. These are also, popular in secure environments because they don't have a hard drive and can be erased with essentially one menu entry to NISPOM standards. Good general purpose scopes. You can see bandwidths ranging from 50 megahertz all the way up to 6 gigahertz in this platform. And the ones to the right, other than the basic model, also have the capability. You see MSO. We'll cover that a little bit later. MSO means mixed signal oscilloscope or digital, like a mini or basic logic analyzer built in to these scopes as well. And that's also common in the Windows-based scopes. Here is our Windows-based scope line. And again, and here we start at 500 megahertz and go all the way up to 110 gigahertz. And yes, that is a real-time bandwidth. So what we're seeing with that is that instead of scopes being used just in general purpose and digital applications, that they're also being used in RF and microwave applications, because you don't have to down convert. We can directly digitize up to 110 gigahertz signal. Another trend here that I'll point out is you guys make converters, obviously, so most of you are familiar with those. The trend has been, at least from a Keysight perspective, is to go beyond the traditional 8-bit A to D converters and the higher performance line. So you see the three newest platforms we have, the MXR, the S, and the UXR, all have 10-bit ADCs rather than the traditional 8 bits of the ones in the middle, the V and the Z. All right, so let's switch on over, and commercials over for now. Switch on over and talk about some oscilloscope basics. In this section, we're going to cover time domain versus the frequency domain acquisition, some basics on sampling, and also bandwidth considerations. All right, so again, not knowing what each one of you do exactly, but I'm guessing you probably do both time and frequency analysis on different types of signals. So time, we're looking at, amplitude versus time, and the frequency domain amplitude, or more common in the frequency domain, is power versus frequency on the x-axis. So time domain applications, versus frequency, the instrument bolded are the most commonly used in this domain. So for time domain, the most commonly used one is what we're talking about today, an oscilloscope. However, modern day signal analyzers / spectrum analyzers, some of those have time domain capabilities through math, as well as network analyzers. Similarly, if you're looking in the frequency domain, the most commonly used tool is a spectrum analyzer. We're now also calling them signal analyzers. A signal analyzer essentially is a spectrum analyzer with some additional software measurement enhancements. But pretty much every oscilloscope being made today has the function right above the instrument on the right, is FFTs. And they are getting better and better on an oscilloscope. So the lines are kind of blurring between the two classes of instruments, especially, again, the oscilloscopes are being broadened now. They can serve as frequency analyzers to a certain extent, and what we mentioned in the very beginning, also in the protocol world. So the oscilloscopes becoming more of a kind of Swiss Army knife of test instruments. All right, and again, how do you convert between time and frequency domain? Well, the most simple way, and the way our instruments do it, is with FFTs. Again, just a mathematical conversion between time and frequency domain. Again, pretty much every scope we make today, except that very basic one that we first showed you, can do FFTs. And it's a question of how much, how much you can do with the FFT, different windows and controls, et cetera, that distinguish the basic ones from the higher performance ones. Same way is that some of our network analyzers and signal analyzers can do an inverse Fourier transform and go from the frequency domain, where they are native, back into the time domain. So again, depending on what you're doing, the behavior you're trying to track down, the problems you're trying to troubleshoot, it might be easier to look at the signal in the time domain or the frequency domain. Again, this is an oscilloscope, but it's doing an FFT. So you see a couple of frequency peaks here. So if you're looking for harmonics or, different main fundamental frequencies, the FFT is the way to go. And you see also, this has some additional capability where we will identify the peaks of the FFT, starting at the highest power and then going down. So you see those identified on the right of the menu on the oscilloscope. All right. So again, I come more from the digital world, more square waves than sine waves, but a square wave is made up of different harmonics. So you see, again, looking in the time domain, we have amplitude versus time, voltage versus time. In the frequency domain, we have power or amplitude versus frequency. So you see the fundamental, the frequency of this square wave is always going to be the highest power in the frequency domain. But again, to reconstruct the square wave, you can see from the slide is what we generally recommend, is that if you're looking at a signal with a fundamental frequency, that we should be able to capture the fifth harmonic. The closer you get to the fifth harmonic, you'll get closer to the actual shape of the signal that you're looking at. And you can see it gets better and better as you go from first harmonic up to the fifth. And by the fifth, you pretty much get a good representation of the signal. All right, again, with an oscilloscope, you can see we have circled the sampling rate. that's how fast the A to D converter is running. You also see to the left of that is the bandwidth. So again, those are two different numbers, and we're going to talk about that. But those are the most common, what they call banner specs of an oscilloscope, the bandwidth and the sampling rate. And again, we mentioned on the previous slide, getting the fifth harmonic is generally recommended to capture the shapes of the signals most accurately. So what you're actually seeing on an oscilloscope screen, as point 3 mentions, is those A to D converter samples, individual digital samples, and then stitched together or in a connected dots mode up to millions or billions of samples. It can give you a continuous waveform shape. And again, oscilloscope bandwidth can either be down as low as 1/3 or third harmonic to fifth harmonic or better, 1/5 the sampling rate. We mentioned, it's recommended to do a fifth harmonic or 5x sampling rate, so 1 gigahertz bandwidth, 5 gigasamples per second. There are some modern techniques, interpolation between actual A to D samples that can drive that number down from 1/5 to 1/3, or again, just getting third harmonic. That could be a topic for another session, some more advanced capabilities like interpolation. All right, most of you who went through electrical engineering, in college know about Dr. Nyquist. He's the one who came up with the sampling theorem and way back in 1928. So, okay, it's not showing on the next slide, but what Nyquist said, as most of you are familiar, is that you need to sample 2 times or higher faster than the highest frequency component of the signal. So if you have to get a unique representation of that signal with its characteristics. So if you're looking at 100 megahertz fundamental signal, that you would have to sample at 200 megahertz or 200 megasamples per second or faster to reconstruct that signal. But that's just to, essentially to reconstruct the frequency characteristics of the signal. As we mentioned in the previous few slides, if you want to visualize it in the time domain, you actually need to sample higher than the Nyquist frequency. So we say, again, 3 to 5x minimum oversampling to reconstruct the signal in the time domain in a waveform format. All right, there's 3 main types of sampling in an oscilloscope. The most common is real-time sampling. So on a single trigger, we're going to digitize and capture all the points in one trigger acquisition. Now, while the scope might run continuously, essentially it's constantly re-triggering and capturing the signal. So you see the bold is the sampling clock, and we're taking a sample point at the rising edge of each clock. And then the circles represent the actual samples, the A to D samples, and then the oscilloscope does the rest, and it connects the dots. With this pre-trigger, so we can actually get data before the trigger point, and we're going to talk about that more later in this type of sampling. And again, the bandwidth depends on the sampling frequency, which we've just discussed here, depending on whether you're 3x, 5x, or higher of the frequency content of the signal you're trying to look at. So the resolution of the points on screen is 1 over the sampling rate. So if I was sampling at 5 gigasamples per second, like we had in that previous slide on the scope faceplate, then these points, the real sampling points, would be spaced 1 over 5 gigasamples per second, or 200 picoseconds apart, and then stitched together. Okay, some of the advantages of real-time sampling, again, you can acquire single-shot events. Often a scope is run continuously, but many times you want to capture a single event, and you can do that with real-time sampling. And again, as I just mentioned, you can actually see data before the trigger, see what led up to a single event. The disadvantage is that if your sampling rate isn't high enough, you could miss points between the actual real samples. Okay. The second type is not commonly used today. It's sort of a hybrid of real-time sampling, but the sampling clock is asynchronous to the input. You can get pre-trigger acquisition. Essentially, but what we're doing is over multiple acquisitions, we are stitching a waveform together. So the bandwidth is not limited by the sample rate, but it requires a repetitive waveform. And the next slide, we're going to talk about the more commonly used sampling method for a repetitive waveform. This is sort of a hybrid between a real-time oscilloscope and a sampling oscilloscope. So again, it's not commonly used today because the real-time and sampling oscilloscopes are good enough to do each one individually. So again, some of the advantages and disadvantages you see on the left side here. But one of the biggest disadvantages, it's really not suitable for high-speed measurements, and that's where sampling oscilloscopes come in, which is on the next slide. So sequential sampling. So again, one sample for each trigger. The biggest disadvantage is you don't have a pre-trigger view of the signal. But we do very small, even increments of delay after the trigger. And again, that delay interval being very small gives us very high timing resolution and very high bandwidth. Before we had a 100 gigahertz real-time oscilloscope, the only way to get that kind of bandwidth was with a sequential sampling machines. Those have been sort of ahead on bandwidth over real-time scopes. Real-time scopes have now caught up, however. So it very accurate waveform reconstruction, again, typically used in high-speed serial applications compared to RF applications, and also in this platform for optical signals as well. If you have optical signals, we have modules in the sequential sampling realm that can directly digitize and analyze optical signals. So again, the advantages, the other thing is, since the A to Ds are not running at ultra high speed, the A to Ds here, we mentioned in the real-time scopes, there's been a push to get above 8 bits. In the sampling scope, we've always had that. For example, our sampling scope has a 14-bit ADC converter. So higher resolution, lower noise in general for a given bandwidth. Again, the biggest disadvantage is the signal has to be repetitive or pseudo-random, where maybe not 100% repetitive, but repeating on a certain interval. And again, in this mode, we have no pre-trigger view, sort of diagnosis. So these are typically used more in validation, characterization type applications rather than debugging or troubleshooting. With that would be used, a real-time scope would more than likely be used in that environment. Right, there's another specialized mode on real-time scopes called high-res mode. So that is used when you have a lot of oversampling. Let's say your signal is only a 1.5 megahertz clock, like we have here in the screen, and you have 100 megahertz oscilloscope sampling at 5 gigasamples per second. To go back to the previous slide, essentially we can run the A to D at full speed and then essentially boxcar average between the samples to get higher resolution and lower noise. And you can see the effect of that on the screenshot to the right. So what you're doing essentially is you're trading off resolution and noise compared to bandwidth. But in this case, I've only got a 1.5 megahertz clock and I have a 100 megahertz oscilloscope in this example. So I've got bandwidth I can trade off. Obviously, if you're pushing the bandwidth specification of the oscilloscope, then you can't use high resolution mode. But this mode is basically in all of our real-time scopes at this point. But you have to manually go into the menu to select it. We are not going to automatically reduce the bandwidth of the instrument. The user sort of has input and control of that. All right, again, bandwidth, that's the other main spec for an oscilloscope. Again, even if you're sampling, in this case, at 5 gigasamples per second or higher, if the bandwidth of the oscilloscope, that's sort of the analog front end before it even gets to the ADC converter. If that's not high enough, you could end up attenuating your signal before it gets to the A to D converter. So that's an important characteristic to note as well. Again, the two biggest banner specs of an oscilloscope are the bandwidth and the sampling rate. So in more cases than not, it's defined in terms of megahertz or gigahertz, but sometimes it's defined often as the rise time of the instrument, and you have to look at that in comparison with the rise time of your signal, which is what we're going to do next. So bandwidth also is called the 3 dB down point. So for that 100 megahertz oscilloscope, it is guaranteed to be 100 megahertz, but it could be 3 dB down. Often our scopes are better than specification, but when you say you have 100 megahertz oscilloscope, it means the signal could be attenuated up to 3 dB at that specified bandwidth. So the way you can tell in this case is, you can actually sweep an RF signal, and the higher in frequency you go, you see the more attenuation you get. You could also actually run an FFT on the scope with no input applied, and you'll see the response of the scope. Now, scopes typically have real-time scopes we're talking about, either 1 or 2 frequency response shapes. You see, with the same 3 dB bandwidth, we can have 2 different responses on a real-time scope. So Gaussian is the ones that were originally developed for oscilloscopes. So they roll off at 40 dB per decade here, a slower roll off, but they start earlier in the passband. With modern day oscilloscopes, and you typically see these in our higher performance scopes, they have what they call a maximally flat response. So you see it's flatter in the passband, but then they roll off quicker, 20 dB per decade. So the maximally flat response is better for a high-speed serial type of signal. A Gaussian gives you, again, a little bit more juice, if you will, beyond the specified bandwidth of the instrument. With our Infinitum, again, our windows are higher performance-based scopes. Typically, they're geared for maximally flat response, where the benchtop ones are Gaussian. But the Infinitum line will actually let you go in and select. You can actually switch between the two, and you can compare your signal characteristics. Again, you've seen that slide that we had before. Again, the general rule of thumb is 5th harmonic without consideration for other advanced techniques like signal interpolation, etc. Great. So if you are trying to look at, let's say, a digital signal or even an RF signal, and you need to know how much bandwidth you have. Again, I mentioned just before that bandwidth can also be expressed as a rise and a fall time. So again, first step, determine the fastest rise and fall time of the device under test. And then from that, you can calculate what the highest signal frequency content is if you didn't already know that. And again, there's 2 different formulas here. And by the way, we're gonna, Leslie is gonna post the slides to to the go-to training site. You'll be able to access these, you know, after the seminar if you like. But there's two different formulas depending on whether you're looking at a 1090 rise time or a 20 to 80. And again, you can, based on the accuracy you want, you can calculate the bandwidth required. And you see there is some variation between a Gaussian response versus a maximally flat. So again, that would also help determine what type of oscilloscope you might pick. So again, you don't have to memorize these formulas or write them down. We're gonna post the slides for these afterwards. So again, here's an example. So what scope bandwidth do I need to measure a signal that have rise times as fast as 500 picoseconds or a half a nanosecond, 10 to 90? Again, you want to look at the fastest rise time you expect to measure. That's going to drive your highest bandwidth. All right, so again, using our friendly formula here, our Ni, or our highest signal frequency content is a gigahertz. So if you're okay with 20% accuracy, which most people are not, then you can buy a 1 gigahertz oscilloscope. But if you want to go down to more the 3% range that most people, you see that requires almost double the oscilloscope bandwidth. So again, how do you know if your scope is too slow or what are the effects of it? Again, using that same signal example, if you were looking at the 100 megahertz signal with a 100 megahertz scope, then you would see a sine wave. But if you really had a faster scope with that rule of thumb 5x fifth harmonic, you can see what you're really looking at is a square wave and not a sine wave. So this is the same signal being put into a 100 megahertz scope versus a 500 megahertz scope. So again, typically, if you do not have enough bandwidth, it is going to round your signal edges. The rise time of the instrument will not be sufficient to measure the rise time of the signal. All right. So we're going to mostly skip through this stuff. So again, when we do this in person, we use this, typically use this 1.5 gigahertz scope. So given the time here, I'm going to, again, just advance through the slides and take a break. Do we have any questions in chat, Cass?
We do not have any questions in chat at this time. Just curious if anybody's is familiar with these scopes that Neil has been talking about.
Yeah, I know there's some of these scopes sprinkled around ADI. So again, I'm going to kind of, advance through these rather quickly. Here again, this family, 1.5 gigahertz, 4 analog channels and 16 logic analyzer channels. And some of the new, more modern features, we can get an arbitrary waveform generator built in. Not the fastest in the world, but it's built into the instrument. In this case, 20 megahertz. We also have models with 50 megahertz waveform generators built in, DBMs, and again, protocol analyzer functions as well. So again, I'm gonna advance through these rather quickly. All right, I see a chat. A yellow graph, 3 dB point. Is that correct? So is that this one you were talking about? Okay. So this is the frequency response of the instrument, of the actual oscilloscope front-end amplifier. So it has, again, we try and be, keep it to 0 dB, no attenuation through most of the passband, and then eventually it will start rolling off like any amplifier attenuator would. Again, there's two main types, the Gaussian response versus the maximally flat. The maximally flat are typically found in the higher performance models, but they can actually switch between the two. Some of that is obviously done in DSP. There's not two physical amplifiers there. So we call it maximally flat because during the passband, up to the bandwidth of the oscilloscope, we're hold that 0 dB line as long as possible, and then it starts rolling off to the 3 dB point. So the 3 dB means the signal would be 70% attenuated. If you put a 100 megahertz oscilloscope, you put a 100 megahertz signal into a 100 megahertz sine wave into a 100 megahertz oscilloscope, it will be 3 dB or 0.707, 70% of the amplitude at that point. But that doesn't mean, it just stops right there. Again, the maximally flat rolls off, the higher you go beyond the specified bandwidth will attenuate the signal faster than with a Gaussian response. Gaussian, you get, again, a little bit more extra bandwidth beyond the specified bandwidth. The trade-off for that starts rolling off faster within the pass band of the oscilloscope. Does that answer the question? Okay. Oh, and as far as swept response, no, that's just a method for evaluating the scope bandwidth. Again, another one is what I mentioned, is that you could just disconnect the input from the scope and run an FFT with no input applied, and it will show you essentially this response with no input applied. All right, I'm gonna move on. Again, we're not gonna cover the controls here. If we were doing this in person, either using this scope or another one, we'd run through the front panel controls here. But you can see as I advance the slides, all scopes have this in one form or another, controls, a trigger section, horizontal section, vertical section, a serial or mask section, an analyze, etc. So, all right, again, I'm going to skip through these labs here. Sorry for that. You'll see, you can sort of see some of the measurements here, like FFTs here. All right. Also, just to point out here that in addition to FFT, scopes have the ability to do mass tests, essentially, or limit tests, where you can put a limit, a tolerance signal. And if the signal violates that mask, which is shown in the shaded areas, in this case, at the bottom and the top, then we will report it as an error. We can stop on errors or keep testing and tell you how many errors and what the failure rate is. And it doesn't just have to be a mask like you see here, a rectangle at the top or the bottom. If you had a pulse, we could do a pulse mask or other types of masks are possible. Oh, there we go. Here's one more around a pulse or a square wave type of signal. And if we do have a failure, again, if you can run in continuous mode, and we will show you the number of failures and the failure rate along with the sigma. All right. So quick question. Let's see if, you don't have to answer this, but how should this scope's bandwidth be chosen? Equal to the signal bandwidth, Nyquist bandwidth, which would be 2x, 3 to 5x, or the bandwidth is irrelevant. And I cheated and showed the answer first. It's C, again, 3 to 5x the signal bandwidth. All right, let's go to triggering. So this is relevant to the real-time scopes. Again, the sampling scopes do not have this capability where you could see pre-trigger. So think of the memory as a rotating ring in the oscilloscope. So it's constantly acquiring data. And if a trigger does not occur, then we will continuously overwrite the acquisition memory. Then when the trigger event happens, then essentially we stop the ring and then we fill the waveform acquisition memory with the aid of these samples. So that trigger event can be put anywhere in the ring. So you can have 100% pre-trigger data, 100% post-trigger data, or anywhere in between. And most scopes, including Keysight scopes, by default, they place the trigger event in the center of the ring. So you have 50% pre-trigger, 50% post-trigger. So again, that's an important point. Again, real-time scopes do this, sampling scopes do not. Sampling scopes, the trigger is always in the center. If there is no trigger, there's no data, nothing is overwritten. And then as soon as that trigger occurs, we delay by very small increments on successive triggers and fill the waveform memory. All right. So again, most scopes by default use what they call basic edge triggering. So you say a positive edge, a negative edge, or either, and you adjust a trigger level. So if you set a trigger level above or below the signal, you have no trigger. So it's either untriggered or it's generally go in auto mode. Hard to see, but it's in the upper right part of the menu here. So it will display something on the screen, but it's untriggered, unsynchronized, etc. More commonly, the trigger is put, rising edge right in the middle, in this case with an AC signal right at the 0 volt point. So you can see that 0 volt is right aligned in the center of the screen. You can raise the trigger level, as we show on the screenshot, to the right. And if you raise it up, you have a trigger point. What's in the center of the screen is a higher point on the sine wave. And again, typically by default, the trigger point is in the center of the memory. So data before the trigger is considered negative time, trigger is T0, and then data after the trigger is positive time. And again, you can control that in the menu of the oscilloscope. You also see trigger control, 50%. Again, that's the most commonly used trigger, where we're triggering right in the center of the waveform. So we have a quick way. When you hit that button, it goes out and takes a snapshot of the signal, and then sets the trigger level right in the middle, assuming it's not a single shot signal. All right, again, there's also two different triggering modes, auto and normal. Again, you saw the auto mode before. If the trigger level on the scope is not set to be within the signal range, the scope supplies its own trigger at a 60 hertz rate. So you'll see something on the screen, but it won't be correlated, it'll be unsynchronized. In normal mode, if you don't set the trigger level within the range of the signal, you will see nothing on the screen. So again, we have both modes of the oscilloscope. You can pick which one you prefer. All right. So more advanced triggering that has been defined. Again, edge triggering has been around since the dawn of oscilloscopes, but now we have some more advanced triggering. Again, I mentioned before, we now have protocol decode capability, including things like I2C, SPI, USB, etc. You can actually trigger on a protocol event, like in this case, an I2C event. You're triggering on the start of frame. And there's even more advanced stuff, which we're going to just quickly step through. Again, if you're looking for rise and fall time violations, we have a rise and fall time trigger. We have various other ones. Again, I'm going to cycle through these. We even have a visual trigger. This is done in software typically. So if you're looking for a glitch, you can actually draw a box here. And depending on the oscilloscope, you can either have up to 4 zones or 8 zones. And you can say trigger if it hits that box, or converse of that, as you see on the bottom right, does not hit that box. So you can zero in on, glitches, certain data patterns, etc. There's lots you can do with the zone or visual trigger. Again, in the interest of time, skip through these. All right, again, we have USB decode triggers. Again, we can cover these because I want to make sure we cover the stuff before we turn it over to Q&A again at the end. So probing. So how do you connect to the signal under test? Okay, in terms of probing, and let me also say, if you can direct connect to the signal with just a cable, a coaxial cable of some sort, you are better off, because the two things that probes definitely add to any signal characterization for any oscilloscope is they're going to add noise over and above what the noise of the oscilloscope is, and cost. Now, we generally include passive probes, which we'll get to in a minute, with the cost of an oscilloscope. But if you need higher performance probes, you'll have to pay extra. Whatever probe you use is always going to add to the oscilloscope. So you have a very low noise application. Again, if you can get away with direct connecting via cable, you're generally better off. So some of the factors that increase as you go up in bandwidth in terms of probing, again, cost, sensitivity, dynamic range, the connection quality is harder, and the amount of development that a company like Keysight has to put in is significantly more. And see from the slide, well, it's not apparent, but 30 gigahertz is about the limit of probe technology today. Once you get above 30 gigahertz, you have to direct connect via cable. All right, some of the things that decrease when you go up in bandwidth. Size is one, because again, the larger size, the higher bandwidth. The capacitance at the tip has to go down. A key thing, though, is in the middle. As you go up in bandwidth, the dynamic range or voltage input capability of the probe typically goes down. You're not going to find a 30 or even a 10 gigahertz probe that can generally do more than 5 volt input. So if you have a higher bandwidth signal with higher input, typically you have to attenuate before you even get to the probe. And in terms of mechanical stuff, durability of connections, they typically are more fragile, and there's less accessories to UT. For example, impel versus solder down, etc. So we got to try and optimize those two things: the things that go up as bandwidth goes up, and the things that go down, to optimize the probe that you would pick. So again, one of the biggest gotchas with high bandwidth probes is the dynamic range goes down over time. So passive probes have higher voltage range or dynamic range, but lower bandwidth. Passive probes typically stop at 500 to 700 meg, where we do make active probes all the way up to 30. But in different bandwidth classes, the higher you go, the dynamic range or voltage input capability does go down with each step in bandwidth class. And if you need even higher voltage, and a typical passive probe is good for maybe 125 volts, AC line voltage. If you need to go above that, or measure current, typically you need a high voltage probe, but you can see those typically are limited in bandwidth, generally a few hundred megahertz. So if you have a higher voltage above a few hundred megahertz, you typically would have to use some sort of attenuator, passive attenuator, before you would get to the probe itself. All right, so this says for the X series, but this really applies to all the different oscilloscopes. So passive probes, again, they've been around forever with your standard ground hook clip. They're good to, depending on the passive probe, 500 megahertz or 700 megahertz. We include that with every scope that we ship. Again, good general purpose probes. When you need more bandwidth or lower loading, you have to go either to a single-ended active probe, if you're looking at single-ended signals, or a differential active probe. And there's different types of those. And again, we do have current probes and other high voltage probes. Again, what you have to consider in addition to bandwidth is loading. Passive probes, again, they're given out with the scopes, and they have high impedance, so lower loading at DC, but they generally have high capacitance. So this is why you can't really get much beyond, 500 megahertz with a passive probe. The capacitance takes over and lowers the impedance of the probe, which increases the loading on the signal under test. So this is for a passive probe, and then the active probe. You see it starts out at DC with an order of magnitude lower input impedance, but it does have much lower capacitance. So it goes out in terms of bandwidth better, but at DC, or close to DC, a passive probe will have lower loading. So again, you have to look at a trade-off, how much your signal will get loaded down versus how much bandwidth you need. And again, we have probes all the way from these passive all the way up to 30 gig. And now you can see loading. Again, here's a 300 megahertz signal bandwidth. That's in green is the actual signal without a probe. And with an active probe, we get pretty close to that signal shape, but a passive probe with the higher loading, you see a slower rise time. We are loading the signal down more. All right, so again, the difference between it at 300 megahertz, the active probe has 600 ohm loading versus the passive probe is down to 50 ohms at 300 megahertz. So you have to look at DC loading versus loading at the frequency that you want to measure. All right, and again, another consideration, and we're getting short on time, with loading is you want to be mindful of your ground lead length, because the longer the ground lead in general, the more loading, and it causes things like ringing. So in the first example, we're using the traditional alligator clip ground lead, 7 inches long. You see a lot of ringing. If we go and take that clip off and use a ground lead right next to the signal path, that little black tip that's been inserted, we have a lot less loading and a lot less ringing on the signal, a truer representation of the signal. So again, the higher bandwidth you need, you have to be mindful of the inductive loading of the ground. All right, you can see that there. So we're close to the top of the hour, and the rest is just a lab. So at this point, I will pause. Here are some, by the way, this picture shows you for the passive probes, the different grounding option. Again, A is what people use by default. It's been around forever. Here are some of the lower inductive loading ground tips that are available with passive probes. And active probes, it really depends on whether you get a single-ended active probe or a differential as to the type of these. There's a family of tips that would go along with that depending on the active probe that you pick. So again, this is part of that. I'm gonna skip through and go to the end here. And we do have, YouTube. We have our own YouTube channel where you can look at some of these topics in terms of if you like to, digest your content in terms of video. You can look at our YouTube channel for the various topics here. Again, we're going to post these slides to the GoToTraining site that we have. I believe everyone who registered will get a link to that. And again, we can, for future sessions, do this in person, customize to a certain oscilloscope model and do labs. We're planning to do a series of these, maybe next time cover arbitrary waveform generators or signal analyzers, etc. So at this point, I will stop here. I think we have a poll question that Leslie's going to put up, and we can also handle the chat. Any chat questions?
Right. So yeah, so we're going to put up the poll question, and I apologize. It looks like I was interfering with some of the conversation there, Neil, when you were speaking. My microphone was causing some problems there, so I apologize to all the listeners for that. If you do have any questions, though, please let us know either in chat or you can email us directly afterwards. And yes, we're just going to share that poll question here and let us know what you think. Any questions or comments from anyone, even in chat?
I do not see any questions in chat, and they can also take themselves off of mute at this point too.
Right.
Yeah, we can. Yeah, if you want to just shout out a question, we're available here.
And that we really appreciate you attending. And again, we can follow up with detail if there was something, since this was one of the first ones we've done, just trying to get a gauge on what people want to hear and what they want to learn about. So we can definitely do something different in the future.
Okay, I think I can close that poll.
Right.
And I'll be sending the links out in an email address to everybody with the slides and the recording.
Okay, great. Well, thank you all for attending.
Yes, thanks everyone.
Okay. Sounds good.
Thanks, Neil.
All right, thanks guys.
All right. Thank you. Have a good day.
All right, you too, Leslie.